Welcome to the Mechanics of Solids lecture series. In this series of videos, we're solving examples considering buckling in columns. Our learning objectives are to calculate P-crit, or the critical buckling load, for axial loaded members in various configurations. And second, to design axial loaded members or systems with axial members for allowable loads and stresses considering both buckling and yield. The first problem is a problem from Mechanics of Materials by Timothy Philpott, Wiley 3rd edition. The problem statement reads, two C12 by 25 structural steel channels with the illustration shown are used for a column that is 35 feet long. Assume pin connections at each end of the column and use E equals 29,000 KSI for steel. Determine the total compressive load required to buckle the two members if A, they act independent of each other, or B, they are latticed back to back as shown in the figure. So our given material properties here, E is equal to 29,000 KSI, and the length of the member is 35 feet. We need to look up the cross-sectional properties, and we're asked to find A, P-crit if this system is unbraced, or the members are unbraced, there's no lateral bracing bars. B, P-crit if it is in fact braced. Okay, if you go to Appendix B in your book, you look up the cross-sectional properties for just the channel itself, and I will simply write the result. You can go to your Appendix B of your text and verify. The cross-sectional area is 7.34 inches squared. Moment of inertia Ix equals 144 inches to the fourth, and moment of inertia Iy equals 4.45 inches to the fourth. Okay? From that, we would infer that the x-axis is strong axis bending, so that must be assuming x in that direction, and y-axis weak axis bending, so that would be y in that direction. Okay. The other thing that you can get from looking up the cross-section properties is the location of the centroid, and we will need that. That is 0.674 inches, and what that's giving is the distance from the centroid over to the edge of the channel, like that. Okay. So those are the properties, and we can proceed to solve the problem. Case 1, if there's no bracing and these two members act independently of each other, then we know that they're simply going to act as two channels, and we can double the moment of inertia. Okay? In this case, we would expect buckling to occur about the weak axis, and that will control. And the weak section property, obviously, we're going to use Iy. Okay? So case part A will say buckling about y controls. And I sub y total simply equals 2 times the given I sub y for that section equals 2 times 4.45 inches to the fourth, and that's 8.9 inches to the fourth. We can use that in the formula for the critical buckling load. P-crit equals pi squared EI y over L squared equals pi squared times E 29,000 KSI times the IY we computed, 8.9 inches to the fourth, divided by the length of the column squared, which is 35 feet. We need a unit conversion, 12 inches per foot, and we're going to square that number. And the whole thing computes to 14.44 kips, and that's our critical buckling load for case A. A relatively small number because the bending a moment of inertia in the y direction is pretty small. Let's see what happens if we in fact brace the members so that they can act together as one composite section. Okay, so in this case we want to locate our coordinate system at the center of both of the members, and we need to consider buckling in both the strong direction and the weak direction. So we'll say find both Ix total and Iy total. And we're going to consider both of them, whichever is the smallest one is going to control. For buckling about the x direction, okay, it is similar to before, that both of the members are located there's at the centroid with respect to x. So the Ix total is simply going to be 2 times Ix for an individual channel. 2 times 144 inches to the fourth equals 288 inches to the fourth. Okay, for Iy total, we have to consider the two members as before, 2 times Iy, but we also notice that the members aren't located at the overall centroid of the system. So we have to apply the parallel axis theorem. And we can do that independently for each member, and the result is the same because they're both located the same distance. So we would add on to the Iy, we would add on the a times d squared for each member. Okay? The area is given, Iy is given. What is d? Well, d is this total distance from the overall centroid to the centroid of the channel. And we see that that d is equal to x bar plus this distance right here, which is 3 inches. So if x bar is 0.674 inches, that's 3.674 inches. So now we can apply this formula to calculate Iy total. 2 times Iy, 4.45 inches to the fourth, plus the area, 7.34 inches squared, times d, 3.674 inches, that whole thing squared, and that computes to 207.1 inches to the fourth. Now in comparing Ix total and Iy total, we see that Iy is still the smaller number, so it controls. And using that, we can compute the critical buckling load with the same formula as before, pi squared E Iy total over L squared equals pi squared E 29,000 KSI, Iy total 207.1 inches to the fourth, divided by our L 35 times 12 to convert it to inches, squared, and that computes to 335.9 kips. So that would be our critical buckling load for case B. As a sanity check, we see that the result we got for case A, when it was unbraced, which was about 14 kips, is significantly less than the buckling load when we brace it. But we expect that because we're getting a lot of increased resistance by moving the overall bending resistance or buckling resistance away from the centroid. So that concludes this example.